Hey, you all! Tonight, we're falling asleep while learning why we can't actually reach the true limit, the ultimate cold, that temperature known as absolute zero. It's a fascinating journey into the very heart of thermodynamics, a deep dive into the rules that govern all energy and all matter in our universe. We'll be exploring the fundamental physics that draws a cold, hard line, a physical boundary that prevents us from ever achieving a temperature of precisely 0 Kelvin. This journey will be slow and deliberate, a gentle exploration of microscopic chaos and quantum certainty, hopefully guiding you into a deep and restful sleep while your mind processes the foundational laws of the cosmos. We must begin our slow, gentle exploration with the corners tone of this entire field, the laws of thermodynamics. These are not merely suggestions, they are universal, unwavering rules that dictate how energy behaves, how heat flows, and why nothing in the universe ever truly stops moving. There are 4 main laws, although they are usually numbered 0 through 3, and each one sheds light on our ultimate quest for absolute zero. Let's start with the 0th law of thermodynamics, a very foundational concept that sets the stage for how we even define temperature. The 0th law simply states that if System A is in thermal equilibrium with System C, and System B is also in thermal equilibrium with System C, then System A is also in thermal equilibrium with System B. Now, what exactly does this mean, thermal equilibrium? It simply means that there is no net flow of heat energy between the systems. If you have a cup of warm tea, which we can call System A, and you put a thermometer, System C, into it, and the tea stops getting colder and the thermometer reading stops changing, they are in thermal equilibrium. If you then take that same thermometer, System C, and place it into a warm bath of water, System B, and the reading is the same, then the 0th law tells us that the tea, System A, and the bath, System B, must be at the same temperature. They are in thermal equilibrium with each other. This law justifies our use of a thermometer, providing a consistent definition of temperature and a method to measure it accurately, which is essential when we are trying to define and approach absolute zero. It allows us to say, definitively, when something is colder than something else. This gentle understanding of thermal equilibrium is the very first step in understanding why we can't reach the absolute cold. Now, let us move on to the first law of thermodynamics, which is simply a statement of the conservation of energy. It tells us that energy can be neither created nor destroyed, but it can only be transformed from one form to another. Think of it as a cosmic bookkeeping rule. In any process, the total amount of energy in the universe remains constant. When we express this law mathematically, it is often stated as, the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Let's spell that out slowly, just the concepts, change in internal energy equals heat added minus work done. This first law is crucial because it governs the energy flow in every cooling process we use. To cool something down, we must remove energy from it, and that energy, often in the form of heat, must go somewhere else. It can't just vanish. We must do work to move that heat, or we must allow the heat to flow out naturally, but the total energy is conserved. For example, in a refrigerator, a cooling system, we do work using electricity, and that work allows the refrigerator to remove heat from the inside and dump a greater total amount of heat into the warmer room outside. The energy is always conserved, it is merely moved and transformed. The quest for absolute zero is fundamentally a quest to remove every last possible joule of internal energy from a system, a process strictly constrained by this first law of energy conservation. Next, we arrive at the second law of thermodynamics, perhaps the most profound and arguably the most relevant law to our discussion of why absolute zero is unreachable. The second law introduces the concept of entropy. Entropy is often described as the measure of disorder or randomness in a system, or more accurately, the measure of the number of possible microscopic arrangements, known as microstates, that correspond to a given macroscopic state. The second law, in its most common form, states that the total entropy of an isolated system can never decrease over time. It can only increase or remain constant. This means the universe, on the whole, is always moving toward a state of greater disorder and greater equilibrium. Heat, the natural flow of thermal energy, always spontaneously moves from a hotter object to a colder object, never the other way around. To make heat flow from cold to hot, like a refrigerator does, we must add external work, thus increasing the total entropy of the universe more than the decrease we achieved in our local system. The second law places a fundamental constraint on the efficiency of all cooling processes. As we try to extract the last vestiges of thermal energy from a system, the process becomes inherently less efficient, requiring more and more work to achieve smaller and smaller drops in temperature, because the entropy change of the system is getting larger, and the cost to bow. That entropy change in the surroundings also becomes larger. The formula for entropy change is critical here. Entropy change equals heat transfer divided by temperature. Notice the temperature term in the denominator. As the temperature of the cold object we are trying to cool approaches zero, the resulting entropy change for any heat removed becomes immense. This is a mathematical harbinger of doom for our quest for absolute zero, suggesting an infinitely difficult task as we approach the final limit, and finally, we reach the third law of thermodynamics, the law that directly and definitively states why we cannot reach absolute zero. The third law states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum or a constant value. More importantly, and more directly, the third law is often stated as, it is impossible to reach absolute zero in a finite number of steps or operations. This is the definitive answer to our video title. The impossibility is not merely a matter of engineering difficulty, it is a fundamental law of physics. As a system gets colder, it becomes exponentially harder to extract the remaining heat energy. The amount of work required to cool the system by one further degree, or even one fraction of a degree, approaches infinity as the temperature approaches 0 Kelvin. The process becomes infinitely inefficient, a cosmic futility driven by the mathematical behavior of entropy. The system never stops moving, and the energy never completely leaves. Let's gently recap the role of the laws of thermodynamics in our quest for absolute zero. The zeroth law gives us a way to define and measure temperature. The first law, the conservation of energy, tells us that the heat we remove must go somewhere. The second law, the law of increasing entropy, tells us that the process of heat removal from a cold object to a warmer environment is inherently inefficient and becomes infinitely less efficient as the object gets colder. And the third law explicitly forbids us from ever reaching that final, unreachable point of 0 Kelvin. These laws form a perfect, logical, and universal framework explaining the limit. Now, let us turn our attention to heat transfer and energy flow, the physical mechanisms by which thermal energy moves. Heat can be transferred in three ways: conduction, convection, and radiation. Conduction is the transfer of thermal energy through direct contact between particles. When a hot object touches a cold object, the more rapidly vibrating, energetic atoms in the hot object collide with the less energetic atoms in the cold object, transferring kinetic energy. This is a crucial challenge in cryogenic experiments. Every wire, every support, every minute residual gas molecule that touches our ultracold system is a pathway for heat conduction to flow back into it from the warmer environment. The rate of heat flow due to conduction is related to the temperature difference and the properties of the material, a quantity often expressed in words as heat flow rate equals thermal conductivity multiplied by cross-sectional area multiplied by the temperature difference, all divided by the length. As we approach absolute zero, the temperature difference between our experiment and the room is enormous, making any conductive pathway a substantial heat leak. We must use materials with extremely low thermal conductivity and ingenious designs to minimize this intrusion. Convection is the transfer of heat through the movement of fluids, like liquids or gases. Think of boiling water, where warmer, less dense water rises and cooler, denser water sinks, creating a circulating current. In the ultra-high vacuum environments required for cryogenic experiments, convection is essentially eliminated, but residual gas molecules, even a tiny amount, can still move and collide with the cold surfaces, transferring heat. This is why cryostats, the special containers built to house ultra-cold experiments, are complex, multi-layered vessels maintained under an intense vacuum, often with multiple stages of cooling to intercept incoming heat. Radiation is the transfer of heat via electromagnetic waves, primarily in the infrared spectrum. Everything with a temperature above absolute zero emits thermal radiation. Even if our experiment is in a perfect vacuum, isolated from contact and convection, the warmer walls of the surrounding container are radiating energy onto the cold system. This heat flow is described by the Stefan-Boltzmann law, which we can state conceptually as radiated power equals emissivity multiplied by the Stefan-Boltzmann constant multiplied by the surface area multiplied by the absolute temperature raised to the fourth power. Since the radiated power depends on the fourth power of the temperature, even small temperature differences can lead to significant radiant heat transfer. To combat this, cryostats often employ multiple reflective layers, sometimes called radiation shields, which are cooled to intermediate temperatures to intercept and reflect the incoming thermal energy, progressively reducing the heat load on the coldest stage. The constant battle against these three forms of heat transfer, conduction, convection, and radiation, is a practical manifestation of the second law of thermodynamics, the law of ever-increasing entropy. Every tiny bit of heat that manages to sneak back into our system reverses the hard-won cooling and drives the system back toward higher entropy and a warmer state. This leads us naturally to the microscopic view of temperature, the concept of energy levels and microscopic particle behavior. To truly understand why 0 Kelvin is unreachable, we must understand what temperature is at the most fundamental level. Temperature, as we measure it macroscopically, is simply a measure of the average kinetic energy of the particles, the atoms and molecules, that make up a substance. NCE. Higher temperature means the particles are, on average, moving or vibrating faster. Lower temperature means they are moving or vibrating slower. The quest for absolute zero, then, is the quest to remove all possible kinetic and potential energy associated with this random thermal motion. Consider a simple ideal gas. The atoms in the gas are constantly undergoing random, chaotic motion, colliding with each other and the walls of the container. The definition of temperature on the Kelvin scale is directly proportional to the average translational kinetic energy of these atoms. We can express this relationship conceptually as average translational kinetic energy equals 3/2 multiplied by the Boltzmann constant multiplied by the absolute temperature. The Boltzmann constant is simply a conversion factor relating the energy of a particle to the temperature of the system. This equation makes it clear that if the absolute temperature, the T, is 0, then the average kinetic energy of the particles must also be 0. This means, classically, that all particle motion would stop at absolute 0. However, the world is governed by quantum mechanics, not just classical mechanics. The energy of a particle is not a continuous variable, it is quantized, meaning it can only exist in discrete, separate energy levels, much like steps on a staircase. The particles occupy these energy levels, and as we cool the system, the particles drop into lower and lower energy states. At very high temperatures, there is a broad energy distribution, meaning the particles are spread out across many high energy levels. As we cool the system, the particles fall into the lower energy levels, and the distribution narrows. This distribution is famously described by the Maxwell-Boltzmann distribution, which shows the probability of a particle having a certain speed or energy at a given temperature. As the temperature decreases, the peak of this distribution shifts toward lower speeds and lower energies. The particles are moving slower, and their thermal energy is lower, but here is where the quantum nature of the universe imposes a hard limit. As we approach the lowest possible energy state, we encounter the phenomenon known as quantum zero-point energy. The concept of zero-point energy is a direct and unavoidable consequence of the Heisenberg uncertainty principle. The uncertainty principle is a cornerstone of quantum mechanics, stating that we cannot simultaneously know both the exact position and the exact momentum of a particle. If we could cool a system to absolute zero, and all particle motion truly stopped, meaning the momentum of all particles was exactly zero, then their position would become completely uncertain, meaning they could be anywhere in the universe. Conversely, if we could confine the particles to a fixed position, their momentum would become completely uncertain, meaning they must be moving. The mathematical formulation of the uncertainty principle states that the product of the uncertainty in position and the uncertainty in momentum must be greater than or equal to the reduced Planck constant divided by 2. Let's state that slowly. Uncertainty in position multiplied by uncertainty in momentum is greater than or equal to the reduced Planck constant divided by 2. Because of this fundamental principle, even at the lowest possible temperature, the particles cannot truly stop. They must possess a minimum, irreducible amount of kinetic energy, known as the zero-point energy. If they stopped, we would know both their position and momentum with infinite precision, which the uncertainty principle absolutely forbids. This residual, inherent motion is the particle's ground state energy, the lowest possible quantum energy level. Even when a material is cooled to 0 Kelvin, the atoms are not frozen solid in place, they are still vibrating with this minimum quantum energy. This zero-point energy is the true, fundamental physical barrier preventing the removal of all energy from a system. The system's internal energy can never be truly zero, it can only approach this minimum zero-point energy level. This constant, unavoidable quantum fluctuation is the essence of why absolute zero is unreachable. We are not just battling engineering and heat leaks, we are battling the fundamental laws of reality that demand a certain amount of energy must exist, even in the coldest possible state. We can lower the thermal energy, the average kinetic energy of the chaotic motion, but we can never remove the zero-point energy. Let's now pivot our focus to the fascinating cooling methods that scientists use to approach, but never reach, this quantum limit. The practical techniques used to achieve temperatures mere fractions of a degree above absolute zero are among the most ingenious applications of physics. One of the most powerful and modern techniques, especially for gases, is laser cooling. This technique works by using the momentum of photons, particles of light, to slow down atoms. The principle is based on the Doppler effect. As an atom moves toward a laser beam, it perceives the laser light to be slightly higher in frequency, or blue-shifted. Scientists tune the laser frequency to be just below the frequency that the atom needs to absorb the photon. When the atom moves toward the laser, the Doppler shift pushes the perceived frequency into the absorption range, meaning the atom absorbs the photon. When it absorbs the photon, it also absorbs the photon's momentum, which slows the atom down. The atom then quickly re-emits a photon in a random direction to return to its ground state, but the net effect of millions of these cycles is a dramatic slowing of the atom's chaotic motion. Since temperature is a measure of this motion, slowing the atoms down effectively cools them. This method can cool atoms from room temperature down to temperatures in the microkelvin range, meaning millionths of a degree above absolute zero. The lowest temperature achieved by laser cooling is limited by the minimum momentum kick the photons provide, a limit often referred to as the Doppler limit or the recoil limit. To go even colder, scientists often rely on a phenomenon called adiabatic demagnetization. This technique exploits the magnetic properties of certain materials, typically salts, at very low temperatures. The process involves two main steps. First, the material is placed in a very strong magnetic field and simultaneously cooled by an external method, like a liquid helium bath, to a starting temperature of a few Kelvin. The magnetic field aligns the tiny, atomic-level magnets, known as magnetic moments or spins, in the material. This alignment is a low-entropy, highly ordered state. The heat generated by this ordering process is removed by the liquid helium bath. Second, the material is isolated from the helium bath in an adiabatic process, meaning no heat is allowed to enter or leave. The external magnetic field is then slowly turned off. As the field is removed, the atomic spins fall back into a disordered, high-entropy state, meaning they become randomly oriented. To increase their entropy, they must absorb energy, and the only available source of energy is the thermal motion of the atoms themselves. Therefore, the thermal energy is drawn into the spin system, and the overall temperature of the material dramatically drops. This is a very effective way to achieve temperatures in the millikelvin range, meaning thousandths of a degree above absolute zero. To go even further, into the true cryogenic frontier, scientists use a technique called dilution refrigeration. This method is the workhorse of ultra-low temperature physics, capable of reaching temperatures as low as a few millikelvin, sometimes even fractions of a millikelvin. The dilution refrigerator operates on the exotic quantum mechanical properties of two isotopes of helium, helium-3 and helium-4. When these two liquids are mixed at extremely low temperatures, they separate into two phases, like oil and water. One phase is a concentrated mixture of helium-3, and the other is a dilute mixture of helium-3 in helium-4. The cooling effect is achieved by continuously drawing helium-3 atoms from the concentrated phase across the phase boundary into the dilute phase. This process requires energy, and the only available energy source is the thermal energy of the system. In essence, the liquid helium-3 atoms are evaporated from the concentrated phase into the dilute phase, but instead of using temperature to cause the evaporation, they use the quantum mechanical difference in chemical potential between the two phases. The continuous flow of helium-3 across the phase boundary absorbs heat, continually cooling the system to lower and lower temperatures. In all of these practical laboratory techniques, we are constantly fighting the influx of heat energy. The cryostats that house these systems are marvels of engineering. They rely on multistage cooling, using liquid nitrogen, then liquid helium-4, then liquid helium-3, often followed by a dilution refrigerator and/or an adiabatic demagnetization stage. Every stage acts as a heat sink for the warmer stages surrounding the coldest core. The design principle is the progressive removal and interception of heat. But even with all this engineering ingenuity, the third law holds true: the closer we get to 0 Kelvin, the smaller the remaining temperature difference, the larger the required entropy change for a given amount of heat removed, and the harder it becomes to extract the final S. Tub-borne energy. This brings us to the real-world limits that reinforce the fundamental physics and ensure the third law remains unbroken. These limits are a combination of material science challenges, the practical impossibilities of measurement, and the intrinsic physical constraints we have already discussed. One major set of constraints is material limitations. Every object, every wire, every structural element used to hold the ultra-cold sample is a potential source of heat. Scientists must use exotic materials with incredibly low thermal conductivity at these temperatures. For example, thin-walled tubes made of materials like stainless steel or certain plastics are used to minimize heat conduction from the room temperature environment. But even these materials conduct some residual heat, and that heat is constantly flowing into the coldest part of the system. The very act of supporting the cold experiment introduces a heat leak. No material is a perfect insulator, meaning a thermal conductivity of exactly 0. The second law of thermodynamics demands that heat will always flow down a temperature gradient, and that gradient exists between the room and the experiment. Furthermore, any vibration or mechanical noise introduced into the system is a form of energy that contributes to the internal energy of the cold sample. The experiment must be isolated from the floor, from air conditioning units, and from external acoustic noise, as all these vibrations can couple into the cold structure and warm it up, representing another unavoidable heat flows. Another significant challenge is measurement. How do we accurately measure temperatures mere microkelvins above absolute zero? Measuring the temperature itself requires introducing a thermometer, and that thermometer must be thermally coupled to the sample. Any thermometer is a physical object, and thus it possesses a heat capacity, which is a measure of the amount of heat required to change its temperature by a certain amount. We define heat capacity conceptually as heat capacity equals heat added divided by temperature change. If the thermometer is to provide an accurate reading, it must be in thermal equilibrium with the sample, meaning it must be exchanging heat with the sample. However, the thermometer itself, even the smallest one, has mass and absorbs energy from its surroundings or from the measurement process itself, thus heating the ultra-cold sample we are trying to measure. The very act of measuring the temperature inevitably adds a tiny amount of heat energy to the coldest system, causing a slight warming and preventing us from confirming the lowest possible state. This is a practical limit that is intimately linked to the conservation of energy, the first law of thermodynamics, and moreover, the thermometers used at these temperatures, such as resistance thermometers or magnetic susceptibility thermometers, rely on some physical property changing with temperature. As we approach absolute zero, the changes in these properties become infinitesimally small and incredibly difficult to measure accurately. The signal-to-noise ratio in the measurement equipment becomes a major hurdle. The unavoidable, inherent random noise in the measurement apparatus can easily overwhelm the tiny, significant signal that indicates the true temperature of the sample. Then we return to the fundamental physical constraints, the immutable laws. We must repeatedly circle back to the third law of thermodynamics. It is impossible to reach absolute zero in a finite number of steps or operations. This is the hard-line, most important constraint. Every cooling method we use, from laser cooling to dilution refrigeration, is an operation, a step. To remove the remaining tiny amount of heat, the process of cooling requires an increasingly large expenditure of energy, of work, and an increasingly longer time, approaching infinity as the final limit of 0 Kelvin approaches. Let's reiterate the link between the third law and entropy. The formula entropy change equals heat transfer divided by temperature shows that as the temperature, the T in the denominator, approaches zero, the entropy change for any amount of heat transfer, even an infinitesimal amount of heat transfer, approaches infinity. To balance this infinite entropy change in our system, the environment would need to undergo an equal and opposite change, which is physically impossible. The process of removing the final joules of energy would require an infinite amount of work input and an infinite amount of time. Therefore, achieving absolute zero is a task that would require an infinite power plant, running for an infinite duration, a clear physical impossibility. Let's spend more time exploring the subtle but crucial concept of quantum zero-point energy and its effect on materials. Think of a solid material, a crystalline lattice of atoms. Classically, at absolute zero, these atoms would sit perfectly still at their lattice points. However, quantum mechanics dictates that they cannot be perfectly still. They must vibrate with a minimum zero-point energy. This is sometimes described as the zero-point motion of the atoms. This zero-point motion prevents the perfect crystalline structure that a classical physicist might predict. The atoms are always jiggling, always moving, always possessing that minimum, irreducible kinetic energy. This minimum energy is not the same as the thermal energy we are trying to remove. Thermal energy is the chaotic, random energy associated with the excitation of particles into higher energy levels above the ground state. It is this thermal energy that defines temperature. The zero-point energy, however, is the minimum energy of the ground state itself. The quest to reach absolute zero is the quest to bring all particles into their ground state, but even in the ground state, the energy is not zero, it is the zero-point energy. Consider a simple harmonic oscillator, which is often used as a model for the vibrational motion of atoms in a solid. Quantum mechanics tells us that the possible energies of this oscillator are given by the formula, expressed conceptually as energy equals the quantity n plus 1/2, all multiplied by the reduced Planck constant multiplied by the angular frequency, where n is a non-negative I. Integer. The lowest possible energy state is when the quantum number n equals 0. Even in this lowest possible state, the energy is not 0, it is 1/2 multiplied by the reduced Planck constant multiplied by the angular frequency. This remaining half unit of energy is the quantum zero-point energy. It is a mathematical necessity imposed by the uncertainty principle, and it is the physical barrier that remains even if we perfectly remove all thermal excitations. The constant, deep-rooted battle against heat flow and entropy increase is what makes cryogenics such a specialized field. To reach the microkelvin and nanokelvin ranges, the millionths and billionths of a degree above zero, scientists must not only use the most advanced cooling techniques, but they must also consider every infinitesimal energy contribution. For example, the simple act of switching on a measurement coil or applying a small current to a sensor will introduce a tiny amount of Joule heating, which is the heat generated by the resistance of the electrical wires. This heat input, though minuscule, is enough to warm the sample above the target temperature. Joule heating is quantified by the formula, power dissipated equals the square of the current multiplied by the resistance. At temperatures near absolute zero, the heat capacity of materials drops dramatically. Remember the formula: heat capacity equals heat added divided by temperature change. When the heat capacity is very low, even a tiny amount of heat added, the heat added term in the numerator, results in a huge temperature increase, the temperature change term in the denominator. This makes the ultra-cold system exquisitely sensitive to even the smallest heat leaks or measurement inputs. Let's review the 4 major cooling methods once more, focusing on how they exemplify the difficulty of the third law. Laser cooling removes kinetic energy by using photons to slow atoms. This is effective, but it is limited by the minimum momentum of the photons and the inability of light to interact with all forms of motion and internal energy. It successfully addresses the chaotic thermal motion, but only up to a point, leaving the zero-point motion untouched. Adiabatic demagnetization works by manipulating the magnetic order, the spins, of a material. By moving from a low-entropy aligned state to a high-entropy disordered state in a magnetically isolated environment, the process draws energy from the thermal motion of the atoms, cooling them. This is an elegant application of the second law and the concept of entropy. But just like every cooling process, it only removes a fraction of the remaining energy. To achieve the next temperature drop, the process must be repeated, requiring a new setup, a new demagnetization, and an exponentially longer time to reach the next infinitesimal temperature step. Dilution refrigeration uses the phase separation of helium-3 and helium-4. The process of moving helium-3 across the phase boundary absorbs heat. This is a continuous process, making it a very effective workhorse. However, it is fundamentally limited by the chemical potential difference between the two phases, meaning there is a minimum temperature below which the process simply cannot run, a limit imposed by the quantum mechanics of the helium isotopes themselves. These methods are designed to remove heat, the energy associated with the random, chaotic movement of particles. But the ultimate barrier is the zero-point energy, which is an inherent, non-removable part of the system's energy. The zero-point energy is not heat in the classical sense, as it is not the energy of thermal excitation, but it is a minimum residual energy that contributes to the total internal energy of the system. Imagine the universe as a massive energy reservoir. We are trying to pump energy out of a small bucket, our experiment, back into the universe, but the pumping process gets harder and harder, requiring an infinite pump to remove the last drop. The exponential increase in the work required to achieve a temperature decrease is the practical implication of the third law. If it took 1 hour to go from 1 Kelvin to 0.1 Kelvin, it might take a week to go from 0.1 Kelvin to 0.01 Kelvin, and possibly a year to go from 0.01 Kelvin to 0.001 Kelvin. The time and energy required approaches infinity as the temperature approaches zero. Let's dive even deeper into the concept of entropy and its relationship with the unattainability of absolute zero. Entropy is directly related to the number of microstates, the number of ways the particles in a system can be arranged while still looking the same macroscopically. This relationship is formalized by the Boltzmann entropy formula, which we can state conceptually as entropy equals the Boltzmann constant multiplied by the natural logarithm of the number of microstates. As a system is cooled, the particles settle into lower and lower energy star TES, meaning the number of accessible microstates. The number of microstates term in the formula drastically shrinks. At absolute zero, a perfectly ordered, pure crystalline substance would, ideally, have only one possible microstate. Every particle is in its exact ground state. If the number of microstates is 1, then the logarithm of 1 is 0, meaning the entropy of a pure, perfect crystal at absolute zero would be 0. However, in the real world, materials are never perfectly pure or perfectly crystalline. There are impurities, defects, and structural imperfections, all of which introduce multiple possible microstates even at the lowest temperatures. For example, if a molecule can be oriented in two different ways in the crystal lattice, even at the lowest temperature, there will still be multiple possible arrangements, meaning the number of microstates is greater than 1, and thus the entropy is greater than 0. This residual entropy, the entropy that remains at 0 Kelvin due to disorder, is another manifestation of the difficulty. Furthermore, the third law is often stated, in a more precise way, to mean that the entropy change for any isothermal, reversible process approaches 0 as the temperature approaches absolute zero. An isothermal process is one that occurs at a constant temperature. A reversible process is one that can be reversed without a net change in the entropy of the universe. The third law essentially states that as you approach 0 Kelvin, all physical and chemical changes must cease to have any significant change in entropy. This makes it impossible to design a cooling process, which is fundamentally an entropy-reducing operation on the system, that can effectively function at 0 Kelvin. The pursuit of absolute zero is a constant struggle against the universe's overwhelming tendency toward increased entropy and disorder. Every engineered cryogenic system is an isolated, non-equilibrium pocket of low entropy that must be maintained by the continuous input of work, a process that simultaneously increases the total entropy of the universe outside the system, fulfilling the second LAW.TO summarized TH. Insurmountable nature of the problem. We are faced with two primary, interlocking constraints: the thermodynamic constraint, the third law. The work required to remove the final remaining heat approaches infinity as the temperature approaches 0 Kelvin, due to the relationship P between entropy change and temperature, as shown in the formula. Entropy change equals heat transfer divided by temperature. The quantum constraint, the uncertainty principle. Even if we could remove all the thermal energy, the chaotic movement associated with temperature, Th. Particles would still retain the minimum, irreducible zero-point energy, which is a mandatory, non-removable form of energy dictated by the fundamental quantum laws of the universe. The atoms cannot stop vibrating due to the strict requirements of the Heisenberg uncertainty principle. These two constraints, one macroscopic and one microscopic, form a perfect physical wall, an impenetrable barrier against reaching 0 Kelvin. We can approach it infinitesimally closely. Experiments have achieved temperatures in the picokelvin range, billionths of a degree above absolute zero. In some cases, specific degrees of freedom, like the motion of an atom along a single axis, have been cooled to a temperature even lower, in the femtokelvin range, which are quadrillionths of a degree above zero. But we have never, and will never, reach the absolute, true, mathematical 0 Kelvin. Let's reinforce the concept of the heat capacity dropping at low temperatures. In most materials, the heat capacity drops off dramatically as the temperature approaches zero, following a characteristic power law, often a cubic dependence on temperature for insulators, known as the Debye T cubed law. If the heat capacity is extremely low, as it is near absolute zero, the system can be warmed very easily. Even a tiny, accidental heat leak of 1 nanowatt, 1/1000th of a watt, can warm the sample significantly. The equation heat capacity equals heat added divided by temperature change is our reminder. If the heat capacity is nearly zero, a finite heat added results in a huge temperature change in the denominator, instantly destroying the ultra-low temperature state we worked so hard to achieve. This practical sensitivity to heat leaks is a direct consequence of the physics that makes the final cooling so difficult. The constant need for insulation and vacuum in cryogenic systems is a practical application of our understanding of heat transfer. The vacuum chamber surrounding the coldest part of the experiment prevents convection and minimizes conduction through residual gas. Multiple reflective radiation shields, sometimes cooled to intermediate temperatures, combat radiation transfer, progressively absorbing the incoming infrared energy from the room temperature environment before it can reach the core. The entire apparatus is designed to increase the thermal resistance along every possible heat path to an absolute maximum, delaying the inevitable thermalization demanded by the second law of thermodynamics. But no vacuum is truly perfect, and no shield is 100% reflective or conductive. There are always a few stray gas atoms, always a few photons that sneak through, always a tiny amount of conduction through the supporting structures. The pursuit of absolute zero is ultimately a philosophical quest as much as a scientific one. It forces us to confront the limits of our engineering and the absolute, unyielding nature of the universe's laws. The universe is hardwired to have energy, to have motion, and to trend toward disorder. We must again revisit the fundamental formula for energy conservation, the first law of thermodynamics, and apply it to a cooling cycle. The concept is that the heat removed from the cold reservoir, which we can call Q cold, plus the work done by the refrigerator, which we can call W, must equal the heat deposited into the hot reservoir, which we can call Q hot. Stated as an equation, heat removed from the cold reservoir plus work done equals heat deposited into the hot reservoir. To make the cold reservoir colder, we need to make Q cold a large, negative number, meaning we are removing heat. This requires an input of work, W. The efficiency of this process is governed by the Carnot efficiency, which sets an absolute theoretical limit on how well any heat engine or refrigerator can work. The efficiency is determined by the temperature difference between the hot and cold reservoirs. As the temperature of the cold reservoir approaches zero, the theoretical efficiency approaches zero, meaning the work input required approaches infinity for any finite amount of heat removed. This is the first law working in concert with the second law to make absolute zero unreachable. Let's summarize the final thoughts on why the temperature cannot be 0 Kelvin. The microscopic picture is one of constant, inherent motion. The macroscopic picture is one of infinite effort and infinite time. The final, insurmountable obstacle is the quantum mechanical requirement for zero-point energy, which is a minimum, non-removable form of energy that exists even in the ground state of a system. This energy is not a flaw in our experiment or a solvable engineering problem. It is a feature of the universe, a result of the fundamental uncertainty inherent in all particles. We are constrained by the formula uncertainty in position multiplied by uncertainty in momentum is greater than or equal to the reduced Planck constant divided by 2. This means momentum cannot be zero, and thus motion cannot stop, and thus energy cannot be entirely zero. The journey to the lowest temperatures is a slow, methodical march toward the ultimate minimum energy state, a state that is just a sliver, an infinitesimal fraction, above TH. True absolute zero. We can continue to cool systems, achieving new records in the nanokelvin and picokelvin range, but the final, definitive 0 Kelvin will remain forever elusive, guarded by the unwavering third law of thermodynamics and the fundamental nature of quantum mechanics. It is a reminder that in physics, even in the realm of the coldest temperatures, nothing truly ever stands still. Everything has energy, everything moves, and the universe has a minimum energy floor that we can never touch. Sleep well, knowing that the atoms around you, and within you, are always in motion, even in the deepest cold. This constant, gentle motion of the cosmos is the final, most fundamental reason why the journey to absolute zero is a quest that will never end. Let us continue to reinforce the scale of this problem by returning to the concept of heat capacity at extremely low temperatures and T. Heat implication for energy distributions. At room temperature, particles are highly excited, spread across many energy levels, described by a wide Maxwell-Boltzmann distribution. As we cool, the particles drop into the lowest available quantum states. The drop in heat capacity at low temperatures is directly related to the limited number of available higher energy states, the density of states. To raise the temperature of the ultra-cold system, we need to excite a particle from its ground state to the next available energy level. Since the energy difference between the ground state and the next available excited state is large relative to the thermal energy available at these low temperatures, it is difficult to promote a particle. Conversely, it is equally difficult to remove the final energy because the system is already so close to the minimum energy level. The formula for the average translational kinetic energy equals 3/2 multiplied by the Boltzmann constant multiplied by the absolute temperature. Re shows the linear relationship between temperature and kinetic energy. To halve the temperature, we must halve the remaining kinetic energy. But as the temperature approaches zero, halving the remaining energy becomes exponentially more challenging because the small amount of energy we are trying to remove is swamped by every tiny heat leak and the intrinsic zero-point motion. We must consider the persistent practical problem of residual impurities and nuclear spins. Even in the purest materials, trace amounts of impurities exist. These impurities can possess their own nuclear spins, the magnetic moments of their atomic nuclei, which are very weakly coupled to the overall lattice vibrations that constitute the thermal energy. Cooling these nuclear spins often requires an entirely separate, specialized cooling method, such as nuclear adiabatic demagnetization, a much more extreme version of the magnetic cooling we discussed earlier. In nuclear adiabatic demagnetization, the nuclei are initially polarized. Meaning their spins are aligned by an even stronger magnetic field at an already very low starting temperature, often achieved by a dilution refrigerator. When the field is slowly removed adiabatically, the nuclear spins become disordered, absorbing energy from the system's nuclear magnetic energy reservoir. This technique can cool the nuclear spins to the nanokelvin and picokelvin range, making the nuclear spin system the coldest part of the entire experiment. However, the thermal contact between the ultra-cold nuclear spins and the main material lattice, the electrons and atoms, is extremely poor at these temperatures. This poor coupling means that while the nuclear spin system is at picokelvin, the rest of the material, the lattice itself, might still be in the microkelvin range. This is an example of a system not being in true thermal equilibrium, a violation of the zeroth law within the experiment itself. Scientists are constantly seeking better ways to achieve thermal contact between these different energy reservoirs, between the nuclear spins, the electrons, and the crystal lattice, to ensure the entire sample is uniformly cooled. The difficulty of this thermal coupling at ultra-low temperatures contributes to the practical impossibility of achieving a uniform 0 Kelvin state across all parts of a sample. Let's gently recap the role of the laws and the core concept of energy. The first law ensures all energy is accounted for. We must remove every last joule. The second law dictates that this removal becomes infinitely inefficient due to the increase in entropy. The third law states the ultimate impossibility. The quantum world reinforces this with zero-point energy, the non-removable minimum energy required by the uncertainty principle. Consider again the formula for entropy change. Entropy change equals heat transfer divided by temperature. The denominator, the temperature term, is the key. As temperature gets closer to zero, the fraction blows up to infinity. This mathematical infinity represents the infinite work required, the infinite time needed, and the insurmountable barrier of absolute zero. No matter how ingenious the engineering, no matter how pure the materials, no matter how powerful the magnets, the universe's fundamental laws of thermodynamics and quantum mechanics simply do not allow a system to ever fully stop its motion or completely shed all of its inherent energy. The quest for absolute zero is a beautiful, necessary failure, a perpetual reminder of the final, unyielding limits of physics. We continue our slow, gentle exploration by re-examining the concept of heat transfer through radiation, which is governed by the Stefan Boltzmann law. The formula we described conceptually as radiated power equals emissivity multiplied by the Stefan Boltzmann constant multiplied by the surface area multiplied by the absolute temperature raised to the fourth power shows a very dramatic dependence on temperature. If we cool an object from 300 Kelvin down to 30 Kelvin, the radiated power drops by a factor of 10,000. This is why initial cooling is relatively straightforward. But if we try to cool from 1 Kelvin to 0.1 Kelvin, the relative change in radiative heat input from the surrounding shield, which may be at 4 Kelvin, is small, and the absolute power being radiated into our sample is still a source of warming. Even if the surrounding radiation shield is cooled to 1 Kelvin, and the sample is at 1 millikelvin, the shield is still radiating. Every photon that hits the cold sample is a package of energy, a quantum of heat, that must be removed by the ultra-cold refrigeration stage. This relentless influx of energy, no matter how small, constantly fights the cooling process. Every operation in the lab, from the movement of the Earth to the cosmic background radiation left over from the Big Bang, contributes a tiny, measurable amount of energy that prevents a system from fully settling to 0 Kelvin. The 2.7 Kelvin cosmic microwave background radiation itself provides a uniform, unavoidable heat source throughout the entire universe. While the 2.7 Kelvin background is relatively warm compared to the lowest lab temperatures, the walls of the cryogenic system must be cooled below this to prevent it from being the primary heat leak. The mere existence of energy everywhere, in every form, from the quantum vacuum fluctuations to the cosmic background, reinforces the impossibility of truly isolating a system from all energy. The concept of thermal equilibrium dictates that heat will flow until all components reach the same temperature. But since the environment is not at 0 Kelvin, the flow of heat, however slow, will always be toward the ultra-cold sample, trying to bring it back up to the temperature of its surroundings. The entire edifice of a cryogenic experiment is a masterpiece of engineering designed to slow this inevitable heat flow to a near standstill, but it cannot stop it entirely. This is the second law of thermodynamics in full, constant, unwavering effect. Let us once more articulate the core constraints clearly and slowly. The absolute thermodynamic barrier, the third law, states that you need an infinite amount of work or an infinite number of steps to see a system to 0 Kelvin. The efficiency of a cooling process approaches zero as the cold temperature approaches zero, as the ratio of work input to heat removed must rise infinitely. The inherent quantum barrier, the zero-point energy, states that even if you could remove all the thermal energy, the Chayat IC, temperature-defining motion, the atoms would still possess a mandatory, minimum energy. This energy is a direct consequence of the wave-particle duality and the fundamental limits of precision described by the uncertainty principle. The residual motion is not heat, but it is energy, and since a system at absolute zero must have zero internal energy, the existence of zero-point energy is the final, non-negotiable physical constraint. Energy equals the quantity n plus 1/2, all multiplied by the reduced Planck constant multiplied by the angular frequency. Even with n set to 0, a minimum energy of 1/2 multiplied by the reduced Planck constant multiplied by the angular frequency remains. The continuous, patient repetition of these concepts is essential to grasp the depth of the physical limitation. Absolute zero is not a temperature we have yet to reach, it is a temperature we are fundamentally prevented from reaching by the basic, unyielding physics of the universe. The entire quest is a testament to the fact that while we can manipulate energy to an astonishing degree, we cannot violate the deepest rules that govern its existence and flow. We have explored the 4 laws of thermodynamics, the mechanisms of heat transfer, the microscopic definite of temperature, the unavoidable quantum zero-point energy, the ingenious methods of cooling like laser cooling and dilution refrigeration, and the practical challenges of material science and measurement. Every single facet of this exploration points to the same conclusion: an infinite barrier stands between us and 0 Kelvin. The slow, methodical process of cryogenic cooling is the physical manifestation of the second law of thermodynamics, the law of increasing entropy. The extreme length scientists go to, the complex, multi-stage cryostats, the hours of careful operation, all demonstrate the exponential difficulty of removing the last molecules of energy. It is a slow, quiet, fascinating battle against the relentless march of disorder, a universal force that will ultimately ensure our ultra-cold experiment, however close to the limit, will remain forever slightly warm. The temperature may drop to a billionth of a degree above absolute zero, but it will not be zero. The internal energy will be reduced to its absolute quantum minimum, but it will not be zero. The entropy will approach its theoretical minimum, but it will not be zero. This subtle, but critical, distinction is the profound lesson of cryogenics and the ultimate testament to the foundational laws of the universe. We can approach the limit, but we can never touch it. Sleep soundly now, in the knowledge that even in the deepest, most quiet cold, the universe is still humming with energy and motion. This perpetual, minimum energy is the signature of our quantum reality. Let us re-examine the cooling methods one more time, focusing on their inherent energy constraints. In laser cooling, the fundamental limit is the recoil limit. When an atom spontaneously re-emits a photon, the photon carries away momentum. This spontaneous re-emission occurs in a random direction, imparting a random kick to the atom, slightly warming it. The minimum possible temperature is defined when the cooling rate from the laser absorption is perfectly balanced by the heating rate from the random spontaneous re-emissions. This is a clear, physical, non-negotiable limit based on the quantum nature of light and matter interaction. In adiabatic demagnetization, the limit is reached when the magnetic system, the spins, becomes so cold that its heat capacity approaches zero, and the remaining nuclear magnetic energy is equivalent to the system's zero-point motion energy. The process relies on the fact that the spin system has a higher entropy than the lattice at a given temperature. Once the two systems are fully coupled and the spins have absorbed all the thermal energy they can, the cooling stops, and the system is left at its minimum energy state, which is still above absolute zero. The dilution refrigerator is limited by the fact that the flow of helium from the concentrated phase to the dilute phase is an evaporative process, but it is not a perfect one. A certain amount of heat is always carried back across the phase boundary, and the process stops working efficiently once the temperature differential is too small. The minimum achievable temperature is a fixed point, a consequence of the quantum statistics of the helium isotopes. This minimum temperature is typically about 2 millikelvin. To go below this, a completely different method, such as magnetic cooling, must be employed. The need to switch methods, to perform a discrete, new operation to achieve a further, smaller drop in temperature, is the practical embodiment of the third law's requirement for an infinite number of steps. We must also briefly consider the impact of gravitational effects on absolute zero. While not a primary constraint, the energy of a particle is influenced by its gravitational potential. If we have a very tall column of gas, the atoms at the top are slightly warmer than the atoms at the bottom due to the minute change in gravitational potential energy. To achieve 0 Kelvin across an entire system, every particle must have the exact same minimum energy. The mere presence of a gravitational field, a universal force that varies potential energy with height, would introduce a difference in the minimum energy state of particles at different locations, further complicating the definition and attainment of a uniform absolute zero. The formula for gravitational potential energy is gravitational potential energy equals mass multiplied by the acceleration due to gravity multiplied by the height. Since height is non-uniform, the energy is non-uniform. Finally, we circle back to the central theme of energy distributions and entropy. At high temperatures, the distribution of particle speeds is wide and chaotic. At ultra-low temperatures, the distribution is extremely narrow, clustered near the minimum energy state. Entropy is a measure of this spread. As the spread approaches the single, minimum quantum state, the entropy approaches zero. The final, insurmountable gap is the distance between the near-zero entropy state we can achieve and the absolute zero entropy state that only occurs at a mathematically perfect 0 Kelvin. This final distance is the quantum zero-point energy, the irreducible minimum required by the uncertainty principle. The constant, quiet, subtle motion of particles, even in the coldest reaches of the universe, is the ultimate physical proof that absolute zero will forever remain an unreachable, theoretical limit.